Hi guys, sorry I couldn't be in today, but I'm still undergoing some tests from when I was sick before. So I have to be back to the doctor's tomorrow. So anyway, I'm not going to be there. And I wanted to get you started on section 5.3, limits at infinity. So you've done first and second derivative tests. Hopefully that went well. You guys can work together and check your answers together to make sure, that you got them right. And if you have any questions, you can consult with one another and I'll clear up anything, any questions that you have on that on Monday. But we're gonna go ahead and move along because this is pretty simple and it involves your knowledge of Algebra 2 a little bit, and I don't think you're going to have a problem with this at all, so you'll still be ahead of the game. Okay, so what we're going to talk about is limits at infinity, and this starts on page 271 of the book. Okay, and what we're going to be looking at is, what is the function approaching as it goes to positive or negative infinity. So the first little, it's not really an example, but this little, I guess, example, we could call it, this function here, 1 over x squared plus 1. If you look at the graph and, you say to yourself, well, gee, what's this function doing, or what's it approaching? What height is it approaching as I get really, 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 really big in the x direction, or as x approaches positive infinity? And what we can see, it's very clear that this graph is approaching 0, a height of 0, right? Likewise, if I want to see, what the behavior of this graph is as I get, as values of x get really, really, really small or approach negative infinity, let's sort of look at the graph and say, hey, it's also approaching 0. So when we want to take a limit or inspect limits at positive or negative infinity, what we're looking to see is, what happens as the values of x in a function get very, very big or very, very small. And in this particular case here, we would denote it like such. We would say the limit as x approaches positive infinity, oops, and by the way, you don't need to put the plus for positive infinity, you just put the infinity symbol and that's good enough, of this function is equal to 0, because that's the height that the graph is approaching way out in infinity land. So, formal definition on the same page in the little gray box. A function has a limit L, which is just some number, like we had 0 above. Okay, that was the limit, it's a number. As x increases without bound, or as x is approaching infinity, we write the limit as x approaches infinity. And by the way, it could be plus or minus, of the function is equal to that number. Okay, if the outputs f of x can be made as close to that limit as we like by taking x sufficiently large. Okay, and likewise we looked at that graph on the negative. So sorry I'm messing around with this. I'm using my document camera and I've not really made too many videos with this, so I'm not that good at it. Go figure. But anyway, the limit as x approaches negative infinity of that same function, we realized that the height of that was approaching 0. Okay, so we could have gotten, had this been a different function, we might have gotten infinity, which is not a number. Okay, it's infinity. So anyway, when we're looking for these limits, we're looking for some kind of a finite number that we can sort of make sense out of. Okay, so let's look at another example, and I'm going to stop using the book here for a second. But another simple function, just move this book over. Another simple function is the function f of x equals to 1 over x. This is also on the next page in your book. But, if I want to take the limit of that function as x approaches positive infinity, I'm not even graphing it. I know what it looks like graphically. This thing looks like this, right? And I know that x is equal to 0 is a vertical asymptote. I also know that y equals to 0 is a horizontal asymptote. But what I know about this graph is as the values of x get really, really big, this graph is going to approach 0, or the limit's going to approach 0. Likewise, in the negative direction, as x gets sufficiently large in the negative direction, it's also going to approach 0. Okay? Well, what happens? Let's think about this for a second, because this is important. If I let x equal to 10, well, if x is 10, then, you know, if I throw that in my calculator, or you guys don't need a calculator for this, but you know it's 1/10, right, or 0.1. And if I divide 1 by 100, so I let x equal to 100, well, it gets a little smaller, right? And if I do 1,000, then that's a little smaller. So what's happening here is as the denominator gets really, really big, then this number is going to approach what? It's going to approach 0. And this is going to be an integral concept in just a minute for you to see. Okay, so whether we're talking about positive or negative infinity on this, the limit's going to be 0 on this particular function, but there are many functions that we're going to have to do a little bit of work to see what's going on. One particular function is from example 2 in the book. So this is from example 2. And what we want to know is what is the limit as x approaches infinity, so just positive infinity in this case, of 1 plus x squared over 2 minus x squared. If I go and plug my infinity in, so just like you did when you had limits as x approaches some number, like 5 or 3, right? You'd plug the number in and see if you could simplify it to a finite number. Sometimes, you know, you got 0 over 0 and that was bad, so you had to factor or something, okay? So I could plug this in. I could go ahead and plug the infinity in, and I'd get 1 plus infinity squared, which is infinity, over 2 minus infinity squared, which is infinity. So what I've got is 1 plus this ginormous number on top, and 2 minus this ginormous number on the bottom. And essentially what I get is infinity over infinity. And those don't cancel to equal 1 or anything, okay? This is a problem, and this is something we're going to study in chapter 10 on how to alleviate this. But for right now, we are trying to find a limit. And so the way that you're going to do it is as follows. You're going to take the highest degree variable in the denominator and divide every term up and down of your function by that variable of the highest degree. So what you have to write for the greater is limit as x approaches infinity. The highest degree variable downstairs is x squared, so I'm going to do 1 over x squared plus x squared over x squared, all divided by 2 over x squared minus x squared over x squared. And then you're going to clean that up. That's the limit as x approaches infinity of 1 over x squared, nothing to clean up there, plus 1, all over 2 over x squared minus 1. Now that idea about, you know, if I divide 1 by 10, I get 0.1, and if I divide by 100, I get 0.01, and on and on and on. The idea is that the bigger the number is in the denominator, the closer I'm going to get to 0. So at this point now, I can plug infinity in. I'm going to have 1 over infinity squared, which is just infinity, so I'm going to leave it like that, plus 1. And likewise on the bottom, 2 over infinity minus 1. What's 1 over a great big number? It's 0. And what's 2 over a great big number? It's 0. So the limit as x approaches infinity is -1 for that problem. Capiche? Let's look at another one. Let's look at the limit as x approaches infinity of x minus 1 all over 2x plus 1. If I go and plug infinity in here, and I can to see what happens, but if I plug infinity in, infinity minus 1 is still infinity, and 2 times infinity plus 1 is still infinity. So I've got this infinity divided by infinity issue again. So what are we going to do? We're going to say this is equal to the limit as x approaches infinity, and we're going to divide every term top and bottom by the highest power of x from the denominator. So there's only one variable, it's x downstairs, and its power degree is 1. So I'm going to have x over x minus 1 over x all over 2x over x plus 1. And I'm going to clean that up. 1 minus 1 over x over 2. Oops, I forgot my x over here. Over 2 plus 1 over x. Now we know that 1 divided by a big number is 0. And at this point I can't clean it up anymore, so I'm going to plug infinity in. I'm sorry, my dog's going a little psycho. Stop, Ella. So I've got the limit as x approaches infinity of 1 minus 1 over infinity over 2 plus 1 over infinity, which is equal to 1/2, because those are both going to be 0. Is that okay? Okay, the next thing we need to talk about real quick is asymptotes. So I'm going to take you down memory lane from Algebra 2. In Algebra 2, you learned some nifty little tricks about vertical and horizontal asymptotes. Okay? So for instance, I don't know, let's just say we'll use a simple function, f of x equals 1 over x. We know that we're going to have a vertical asymptote at x is equal to 0. We know that if we want to find vertical asymptotes, then we set the factors of the denominator equal to 0 and we solve, right? And those will give us our vertical asymptotes. And if we want to find the horizontal asymptotes, then all we have to do is take the numerator and solve for x. Okay? So when you were in algebra, you learned a couple of things. If the degrees of the numerator were greater than the degree in the denominator, so a little example, I don't know, suppose you have x squared over 2x. The degree of the numerator up here is bigger than the degree of the denominator. Well, you can see on this thing that you could cancel an x for an x and have x over 2, right? So whenever the degree of the numerator is bigger than the degree of the denominator, there's going to be no horizontal asymptote. So I'm just going to denote that as HA for horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, so I don't know, let's say 1 over x, okay, then the horizontal asymptote is going to be the line y equals to 0, just like this function up here. And if the degree of the numerator is equal to the degree of the denominator, so maybe 3x squared over 2x squared, what we know is that those cancel because they're the same. And so what we're going to have is a horizontal asymptote at the ratio of the leading coefficients. So we're going to use the ratio of leading coefficients. This is the highest degree in the numerator and its leading coefficient is 3. This is the highest degree of the denominator and its leading, so it's the leading the number or the coefficient multiplied to it is the leading coefficient downstairs. And so when the degree of the numerator equals degree of denominator, then the horizontal asymptote is just going to be the ratio of the leading coefficients. Okay, so let's have a look here. Let's look at the limit, the function f of x equals x to the 4th plus x squared over x to the 4th plus 1. This is in the book on the bottom of page 273. And the first thing I want to think of is, are there any vertical asymptotes? Well, there aren't, right? Because I can plug in any number I want for x and I'm not going to get a 0 or anything weird. So I would say there are no vertical asymptotes, or that there are none. For the horizontal asymptotes, I'm going to use what I learned from algebra. What I notice is that the highest degreed variable in the numerator is x to the 4th, and the highest degreed variable in the denominator is x to the 4th. And so I know we're going to have a horizontal asymptote when y is equal to 1. So y is equal to 1 is the horizontal asymptote. I should put this here too, just for notes. Okay? And you can see what that graph looks like. It's a little bit complex. It's at the bottom of page 273, and you can clearly see that horizontal asymptote, the graph is approaching a height of 1. All right. The other thing I could do here is, you know, if I wanted to take the limit, right, I could say the limit as x approaches infinity of x to the 4 over x to the 4 plus x squared over x to the 4. So what I'm doing is this little trick where we divide up and down by the highest power, right? So using a limit, that's equal to the limit as x approaches infinity of 1 plus 1 over x squared all over 1 plus 1 over x to the 4th. At this point, I can't simplify that anymore, so I would plug infinity in for x. So I'd have, you know, 1 plus 1 over infinity squared, which is infinity, 1 plus 1 over infinity to the 4th, which is infinity. So I can find my horizontal asymptote to be at y equals to 1. So we can use limits to find horizontal asymptotes. But what it's essentially boiling back to is this thing right here. So you don't even really have to use them unless you're asked to show it using a limit. Okay. Now, by the way, this graph, so I'm just going to make a quick little sketch of this graph. Oops. And I'm just copying this from the book, but it looks something like this. And, you know, this is 1 here. There's your horizontal asymptote at y is equal to 1. What I did was I took the limit as we're approaching positive infinity. However, I also need to check it out when it approaches negative infinity. Now, clearly from the picture, I can see that it's 1, but if I had to demonstrate it with a limit, and I also have to say the limit as x approaches negative infinity. And guess what? It's the same thing. I would be performing the same exact division, you know, top and bottom every term by the highest degree variable in the denominator. So what I'd end up with is this thing still. And guess what? If I plug in a negative infinity and I square it, I'm going to get a positive infinity. Likewise here. So I'm still going to get a horizontal asymptote of 1. Okay? Now, for the vertical asymptotes, you know when you have a rational function. So, let's see, something like this. You know from algebra that you can rewrite that as 1 over x plus 1 times x minus 1, and you take each little factor and you set it equal to 0 and you solve for x. So you know you're going to have vertical asymptotes here at x equals to plus or minus 1, without a shadow of a doubt, right? But let's suppose we want to use a limit, okay, on this. Well, you know, I would say the following. I would say that we know that 1 over f of x is equal to x squared minus 1. And if I take the limit as x approaches 1, why am I choosing 1? Well, because if I solve this thing, then I'm going to have this equals to 0, so x squared equals to 1, and when I take the square root I get plus or minus 1, right? So I have to solve, or I have to take a limit for each case. So the limit as x approaches 1 of this thing is 0, right? If I plug a 1 in, I get a 0, there's no problem, that's the limit. And I would also have to write the limit as x approaches negative 1 of the same thing, because there's 2 cases. If I square negative 1, I'm going to get a positive 1. If I subtract 1, I'm still going to get a 0. So the limit is going to be equal to 0. In other words, the graph's going to approach 0 to the left and to the right of 1. Okay, and then again, I didn't really have to go through all this. I know if I wanted to make a quick graph here of this function without a calculator, I know using some algebra that at positive 1 and negative 1, I'm going to have vertical asymptotes. So terrible dotted lines, I know. find another color. And am I going to have a horizontal asymptote? Well, let's say the degree of the numerator is smaller than the degree of the denominator, so yes, the x-axis, or the line y equals to 0, is going to be a horizontal asymptote. Maybe if I had a few more features, I would know that this graph is going to look something, and this is terrible, but something like that. I can get an idea of it without even really having to take a limit at all. Okay, so one more example on this stuff. Let's see. So this is going to be number 12 from the book. The function is 1 over x squared minus x, and they want you to find the vertical and horizontal asymptotes. Okay, so look, again, I know this is 1 over x times x minus 1. I know a couple of things. I know that the degree of the numerator is smaller than the degree of the denominator, so I know that I'm going to have y equals to 0 is a horizontal asymptote. I also know that if I set each one of these factors in the denominator equal to 0 and solve, I'm going to have vertical asymptotes at x is equal to 0 and 1, right? So, you know, here's my coordinate plane, and I know that the x-axis, y equals to 0, is going to be a horizontal asymptote, and I also know the y-axis is going to be a horizontal asymptote, and I'm going to have another horizontal asymptote at x is equal to 1. Now, I may not know how to graph that thing. You know, I might have to plug in some numbers, plot some points, and connect those points with a smooth curve, but we don't do that in calculus. We just wanted to know what they are, and there they are. Okay. Now, I could do this with a limit, but there, again, there's really no need to. But you could. You could do it with a limit. You can see what the behavior of the graph's doing. Again, you know, you might want to write this as 1 over f of x and bring this upstairs, just like I did with the last example, and go ahead and figure out what the limit is, so where it's approaching, to figure that out. And in fact, let me just grab a book real quick. I'm going to show you something. I'm going to show you, this is section 5.3. Here it is. So that was number 12. I'm going to show you that in the key, I'll bring this up more, or in the solutions manual, the picture of the graph's there, so that's nice, because I have my calculator, but it's not handy. I didn't take it out for this. But here's that problem, and you see what they did. They did exactly what I did. The vertical asymptotes are the lines x equals to 0 and x equals to 1. To determine the horizontal asymptote, we evaluate the limit. Okay? So again, you can leave it just, I prefer this method, just leave it as it is. Don't write it as 1 over f of x. But notice here, they wrote the limit as x approaches positive and negative infinity. Okay? So you're testing both sides, and you can do that. We're going to divide up and down by the highest power of x, so that means we would divide up and down by 1 over x squared. In the numerator, that stays. In the denominator, x squared divided by x squared becomes the 1, and then x over x squared becomes 1 over x. And so now if we plug in positive infinity, we have 1 over a giant number is 0 over 1 minus 0 again. We get a 0. So it shows you right there that the horizontal asymptote is going to be the x-axis, or the line y equals to 0. Alright, so that's it for limits at infinity. And what you're going to do, you're going to complete page 275. You're going to do 1 through 19 odd. Okay? Sending love. Have fun with it. See you on Monday. Have a good night.